So, good evening, everyone. My name is Ritesh Jha, and today I'm going to talk about the intraseasonal oscillation mode and the drivers of the poleward movement of LF and HF also. So, first I'll introduce what is intraseasonal oscillation modes, and then I'll discuss two papers in which they talk about the mechanism of LFISO, the mechanism behind the poleward propagation of LFISO, and also the mechanism of HFISO. And this, I'll talk about the clustering I have done based on the intensity of LF and HF ISO and how the background condition changes in very high HF years and very high LF years. So, intraseasonal variation has been studied using two approaches. First, using the spatial events such as active and break space, and the other one is being done by using superposition of waves or spatial patterns, which is called intraseasonal oscillation modes. So two dominant modes which comes up is first the HFISO, which has a time period of 10 to 20 days, and LFISO, which has a time period of 20 to 60 days. If we talk about the basic structure of LFISO, it's basically eastward. If you look at phase 4 to phase 8, there is a eastward propagation at the tropics, the positive anomaly. And when it reaches to Indonesian coast, it kinds of bifurcates in two regions. One goes northward and one goes southwards. And there is a poleward propagation thereafter. So this is the typical structure of LFISO, which has a time period of 20 to 60 days. This whole period comes up really to around 40 days. And when we look at this HFISO, so here also this kind of eastward propagation is also visible at the tropics, but intensity is low. And the second, there is a westward propagation. If you look at this star, this shows the maximum intensity of positive anomaly at the Bay of Bengal, and it kinds of gets bigger and moves westward. And there is a poleward propagation along with it. If you see this star, it goes here, and then there is a poleward propagation. And also there is a eastward propagation also at the subtropics region here. If we look at this spiral, there is also a maximum positive anomaly which goes kind of eastward along with this region. So if we talk about our first paper, which shows that this poleward propagation in the LFISO is basically because of this sea surface temperature gradient, positive meridional temperature gradient, rather than just anomaly. So they calculated the meso index using OLR. So what they have done, this is the negative OLR contours here. And at day 0, they consider the convection center is around 10 degree north. And this is at CD, is a SST anomaly. Here we can see that this positive anomaly, warm SST, kinds of leads this convection center by around 10 days. And this is the spatial pattern, which is also shows that if the convection center is around 10 degree north, there is a cold SST is behind the convection center and ahead, and north of it is the warm SST. This is the SST gradient. Again, the convection center at the contours we can clearly see using OLR. And here, if we see this plot, this maximum SST gradients kinds of leads by 1 or 2 days. And here, this is the convection, actual convection, what is happening there is kinds of leads by 3 to 4 days of this convection center. Now, what actually happens and how this leads to the poleward propagation of this convection center. So first, what they found is during this warm SST, which is ahead of convection center at around 10 days, with a lead of 10 days, what happens, it kind of destabilizes the atmosphere, depends the PBR, planetary boundary layer. along stronger vertical mixing. Now there is a concept called vertical mixing mechanism. Due to this, during this period, what happens that momentum from the upper winds comes to the surface, accelerating the surface winds. Due to this, the northerlies from the north of it, which can be seen here. So this is the plot at day -5 when the convection center reaches the 10-degree north. And here at PBL at around 850 between this region, we can clearly see strong northerlies from 20-degree north to 10-degree north. Due to this and this temperature gradient, this normally leads to the convections ahead of 3 days ahead to the convection center. And in this way, the convection propagates northward. This is tendency of meridional wind. This plot is tendency of meridional wind. Here also, the negative tendency means the northerly kinds of getting accelerated. And this, we can clearly see, this is the convection center. Along the convection center, there is a positive dV by dt, which means that northerly is weaker around the center, but like 10 days ahead, from 5-degree turn to 20-degree north, we can see that the northerly is kind of negative. dV by dt is negative, which kinds of picks up the northerlies. So coming from the north is getting accelerated. And they also calculated the transport from aloft to surface of momentum is using the VMT. In this, they calculated this part. Again, it can be seen that it's getting positive. By positive means the momentum is being transported from upper layer to the surface. That's why this northerly get accelerated. So in order to get this theory supported by the model experiments, what they have done, they run the model, atmospheric model. This is the control experiment, which is forced by the climatological daily SST. And then forced one, they included the SST gradient, meridional positive SST gradient, along with the intraseasonal SST anomalies. And we can see that this convection, which happens to be 0.06 per day, gets doubled in the forced experiment. We saw that this 50% increment here is because of SST gradient. They also calculated the correlation between, so here is the meso intensity is the vertical velocity at omega at 500 hectopascal. It's coming out to be negative as omega is negative at when there is a convection is there, according to ERA data. So it shows that with the SST meridional gradient, the correlation is around 0.56, but with the anomaly is 0.17. If you see the correlation is very low. So if we summarize the mechanism behind this northward propagation, is just because this warm SST along with the positive gradient changes the PBL wind. Now the vertical winds momentum from aloft kinds of gets to the surface, which kinds accelerates against the northerlies, which makes the low level convergence ahead of the convection center. And in this way, now this, after 3 days, the convection center reaches to the location of convergence. This is kind of time period. Now, when we look at the mechanism behind the LFISO, which is also has a name quasi-biweekly oscillation. So basically what happens here, so in this paper, they talked about not the westward part, but the northward propagation of this north-westward propagation of HFISO. So they found that below south of the 20-degree north, the barotropic vorticity signs of picked up, and above 20 degree, at around 20 degree, HSS, surface sensible heating, and the moisture advection plays the driver of this northward propagation, and above 20 degree, SHS picked up, or SHS becomes an important driver of the northward propagation. So first they found the moisture part. So here the green part shows the positive advection of anomalous moisture gradient by the mean wind, and the pink one is advection of the mean moisture gradient by the anomalous wind. Here we see at around minus. So here day 0 means the convection reaches at 27 degrees. This contour shows the positive atmospheric apparent heat source. Whenever there is a region with the positive HF, is kinds of so there is a convection going because of the heating. So the contours reaches this 27-degree north is been called as a day 0, and it shows that when this convection center is around 15-degree north, this green, which is this term, is kind of ahead of the northward, ahead of this convection center, which becomes the driver of this northward propagation of this convection center until 20-degree north. And here is the column integrated vorticity anomalies, which is in blue. And here the red one shows the sensible surface sensible heating. Again, if we see at around this region, when the convection center is around 14 degree north, this blue part is little bit ahead of this northward propagation, and above the when it reaches the 20-degree north, this sensible heating kinds of picks up. To establish this part, what they did is first created the heat source around the equatorial western Pacific, and then along with this heating source, they reduced this sensible heating to 50% to check whether the northward propagation is because of this sensible heating or not. In order to get this heating source as western Pacific, because of this showing that the HFIs or the quasi-biweekly originates mainly from this region, and along with the tropics, westerly Rossby waves, it comes eastward to the north of Bay of Bengal, and then here the northward propagation starts over the Indian region. So that's why they created this heat source in order to generate the HFISO. Now we can see that just on heating, the northward propagation, we can clearly see this vertical line shows the region between 20-degree to 27-degree north. And when it switched, when the sensible heating is being reduced to 0.5, the northward propagation begins. So they show that this sensible heating is kind of drives above 20-degree and above 20-degree north. Now the key points is south of this 20-degree north, the northward propagation is mainly because of this barotropic vorticity effect. The north, above the around 20-degree north, moisture layer is moisture advection is kinds of plays dominant role, especially this mode. And the sensible surface heating becomes some important driver above 20-degree north. In order to understand how this LF and HF kinds of modulates the Indian rainfall also, what I have done is I have made 4 clusters based on the intensity of LFISO and the HFISO. If you look at this cluster 3, the cluster 3 imposes that this is the years which has a maximum LFISO intensity and the minimum HFISO, and this cluster 4 has a maximum HFISO. It has been seen that when there is a very high LF and low HF is there, the overall rainfall over central India is 92% of the long-term. When there is a HFISO, the mean rainfall becomes 112% of the long-term of these years. So in order to understand how the mean picture plays behind the roll, so this is this 4 is the seasonal mean of the years of the particular clusters for 850 hectopascal wind, and this is 200 hectopascal wind. So if we see cluster 4, which has a minimum LFISO and maximum HFISO intensity, it's strongly westerly at the low level, which kind of explains why rainfall is high, because advection of moisture from the Arabian Sea is very high. And when we see this very high HF, cluster 3, there is strong steady over the lower region, surface area. It's near the surface. Now, when we look at this 200 hectopascal, at around this cluster 3, we can clearly see there is a Tibetan high is there, and in anomalous side, there is a Tibetan high, which makes the easterly above the wind. If we combine these two, which kinds of say that the vertical shear during these years in the wind picture is very strong. That's why higher rainfall. When the intensity from 2.59% LF mean raised to 12.69%, this Tibetan high starts weakening up. When it raises to 37.51%, this Tibetan high becomes upper tropospheric low. And it gets even stronger when it reaches to 50% variance. So the mean picture of this, if we see, kind of dominated by LF and HFI. So why we may study these features? Because many scientists have been shown that predicting actual rainfall is kind of difficult if we compare to these filtered modes. So if we are able to know the intensity and the phases of this HF and LFI, so what information we can get? So if we look at next, so this is wind anomaly average over 500 to 300, and in shading it's a specific humidity. And clearly we can see the wind is towards north west, towards northwest, which kinds of act as a barrier to the mid-latitude intrusion, also drier intrusion. Again, one reason why there is a higher rainfall. And if we see the wind is southeasterly in this region, along with the negative anomaly of specific humidity, which kinds of leads to the intrusion also. So if we say that this LF and ISO, first of all, manifest differently in different years and could be tied to the wider conditions such as mid-latitude intrusions. So, yeah.
Frequency is 10 to 20,
HFI.
yeah, how many days? So periodicity, you want to go to periodicity of HFIs.
10 to 20 days.
But what about from 5 to 7 days? There
So synoptic disturbance. No, so not in this analysis.
I don't think that is also okay. The has to pick some of it, not the structure.
No, not the structure, but he kinds of picked up in a trained analysis. He found that in past 2-3 decades, the intensity of LFISO is decreasing and it's been compensated by the intensity of synoptic disturbances. So it's because synoptic disturbances kinds of, if we see the results of this, that the years which have a maximum LFISO tends to have a lower rainfall. And if we have a max, since LFISO decreasing, so it could be leads to the synoptic disturbances increasing. So it's one of the analysis he did in his paper.
The PE had something, this is the mechanism. Yeah, so what is that magnitude of SST?
Here, SST anomaly is not there. Yeah, this is the.
Look at that anomaly magnitude, this is so tiny, right? So how can this be the core in, given a mechanism of quantum propagation? And also given that with a monthly mean sea surface temperature, with only AECM, even right, we should be able to get quantum propagation. So this can be the core of the mechanism of the propagation and how.
So monthly sea temperature is basically opposite what we get. It's like heating near the equator and cooling at the higher latitudes. Could be,
So I'm trying to say, so whatever is
it's opposite what we,
the point is that we not keep the international oscillation in the surface temperature. You get counter propagation, right? And also given that in observation it is so tiny, how can it be at the core of the mechanism of the propagation? That's my question.
Only about 2.
Yeah,
Yeah.
I think just maximum 0.2. Isn't it?
I mean, here what this shows that this could lead to the strong northerlies.
They are all the aftershock. These are all these are all consistent with each other. That's all, nothing. Isn't it? Because I mean, we don't need that. That's what it is. So these are all the effects. Surface temperature is only an effect of that. That's not a cause.
There are other like thermodynamic based propagation mechanisms which are explained, assisting gradients also, the asymmetry in heating. If you go back, maybe you have to go back to the 90s, at least we go with Oscillation and JS. Where they stage the asymmetry of the convective heating, which is kind of driving propagation. So that is more realistic to me than this assisting gradients. And assisting gradient, depending on what you mean assisting, it's a very non-linear effect. Your SST is about 28 or 29, it really converts. If you're at 26 and you're speaking of 0.1 or 2 degree SST anomaly, it doesn't really convert. So there's no single straightforward relationship within this particular topic. It's more like there could be thermodynamics could be playing a more significant role than just the dynamics that the
Yeah. Just because that, for example, monthly SST you provide in an ECM, you get not the production state. You only make DEC. Understand? So it must be coming fundamentally. FST may be changing the character to some extent, but fundamentally it is atmospheric. Thank you.
Okay, today I start my presentation with a nice color graphic generated by Viber, who is here. And this is to look at the last 10 years. Okay. So the last 10 years, daily data he has taken from IFD. This is a core monsoon zone, right? Yeah, this is a core monsoon zone. And I don't know how many of you at the work can see it. It highlights lots of things at one glance. Because it highlighted different colors in different months. But of course, daily data means a lot of information is packed here. So some of you may have problems and highlight to you interesting things about August 2023 when we had a huge break that shows the difference between 2022 very clearly. Okay? And the key thing I want to notice here is that only mainly July and August you get this daily monsoon core rainfall much about 20. Okay? June, of course, you never get it. But in the recent days, September has started showing some heavy rainfall days. Okay, that comes out. But this is a very dense data because you are doing daily. So let's look at pentan. Okay, pentan is a little more easy to follow. Okay, but the data, I mean, similar conclusion can be arrived at about September, for example. Look at September 2015 when we had a drought because of El Nino, and what happened last year. See the difference. So September are getting more and more rainfall than in the previous 10 years ago. Okay. Because there was one September, you remember, 2019 was very unusual. So this is interesting. So I thought one can also look at it if you don't like this packing in terms of month separation. So you can look at it and look very confused, except one I want to highlight. In 2019, okay, July, June, July, August, September, it brings out clearly the beginning of the monsoon around the middle of July and then recovery. Now, why I'm showing this? Because this is what happened this year. This year had a fairly good monsoon till July 15th. Now it's beginning to slow down. So you'll see that. So it's worth looking at some of the pictures, and it also shows the value of good color graphics. Okay. Now, the thing about this year's monsoon is up to 22nd, I think the 23rd right now, suddenly the excess rainfall has gone down to just 3%. Okay. So it was much higher, it was around 10% the first week. Slowly monsoon is slowing down. Still, of course, the cumulative is around 5.5%. And you could notice that Peninsula is getting slightly better now. It's not as bad as East and Northeast India. Okay. And this is seen in the All India clearly from about 15th, we have been seeing steady reduction in the monsoon rainfall. And this is shown clearly in the monsoon core zone. And you do a standardized anomaly, and you can see that that nice period we had in the beginning of July ended. It became a little weaker. Now, for the last 4 days, it has been below normal, and on one day, it hit 1 sigma below normal. Okay, so there is a hint for the decline. And if you by GFS, it got the decline right, except I would say it got the decline right, but this increase really did not happen. Okay, and you'll see further decline in the coming days. Now let's look at a few one-day forecasts because I want to look at the spatial patterns. So I would say that I used to show anomalies, but I find anomalies misleading. The only trouble with this figure from IMD is that color bar is highly nonlinear. Okay. Now that's understandable. You cannot have a linear thing for rainfall, things. But I don't like it because they go from 0 to 2.5, 2.75, fine. Then they jump to 35, which I think is they are going further and then goes to 100. So this is all 100. Okay. And this color bar done by the agriculture groups, I think is much better. They are also increasing, but more gradually. Okay? And they're using more colors. So here this peak rainfall around 70, 80 millimeters is shown here. Here it's showing more than 100 millimeters, but they got the location right. Okay? But in this region, I think the forecast was a little too high. Okay? But the locations are roughly correct. And also, I would say they got roughly the fact that this region is not rainy. This is for 19th, okay? Like the 20th, I would say is done even better. This clearly reproduced. This is well reproduced. And this long line also is quite good, okay? Now let's look at 21st. I would say not as good, but this one is extended where it is not. But they got this right and they got this right. Okay? And along this, so the heavy rainfall and circuit, and that more or less was captured. Now this is 22nd, that is yesterday. And I was curious about this particular prediction here of very heavy rainfall, about around 100 millimeters. That doesn't quite come up here, although the color bar is not very useful because they go 35 to 105 one color bar. So maybe this is close to that, quite possible. So again, I want to highlight how important it is to choose your color bar for rainfall very carefully, depending on what you want to highlight. Okay, so if I had a choice over this, I would have chosen a similar color bar. Then one would have got a better thing. But maybe you don't have this year's data, right? You have data till last year. Okay, maybe then I would ask you to replot it this way. Maybe next year we can. Huh?
behind the IMD chooses that? I read somewhere that it's based on the drought years, flood years.
Yeah.
Chosen,
Okay.
But is there a reason?
Okay. Now, this is a forecast made on 16th of July for 26th, which is coming this Thursday, right? Yeah. Friday. Okay. Now, what I was interested in is forecast made on 16th days is very high rainfall here. 10 days in advance. But the next forecast, 3 days later, will disappear. So all you should know is that with today's GCMs, you cannot trust heavy rainfall even 10 days in advance. You can't. Because it disappeared completely. Okay. So that's a warning that heavy rainfall forecast is good only 2 to 3 days in advance. And even there, intensity may go wrong. Now let's look at what forecasts are made 1 day in advance. Yesterday, they made a forecast for today. Okay. And this is not quite here. It's there, but not quite as big. But I'm impressed by this part. This IT season over the Bay of Bengal is almost correctly reproduced. Okay. So there's a clear message there that over ocean, your SST is fairly well known and your model will assimilate it correctly. You will get the locations of IT season as well as rainfall very accurately. Over land, it's much more difficult. So this was, anyway, this I saw it 10 days before. I think it's not that this picture, but I saw it. Maybe we'll show it next time. So this was visible in the forecast made on, I think, 13th July or so, if I remember correctly. Yeah. Now, there are papers published now about heavy rainfall events in Uttarakhand, because there was one famous one all in November, which I got caught here, right here. This was the Kedarnath episode, and this is an older one. And WRF is able to forecast quite well. Okay. So this is one paper by IITM group showing that WRF about 5 days in advance is able to consider forecast not 1 day rainfall, but average over 4 days or 5 days. Okay. Now I want to talk about an interesting issue related to climate change. So all of you know that due to global warming, heavy rainfall is increasing. Okay, and so that's shown up in this mainly due to water vapor. This is the specific humidity. For a 1% increase in CO2, it's going up at the rate of 6.7, close to triple equation. That's the one. Okay, that is the humidity. The rainfall is going up much more slowly. Okay, almost 1/5 of that. Okay, and why is that? The explanation now is that the moisture convergence, okay, is going down. Okay? So the point is that lot more moisture is available as occurs, but rainfall is not going up that rapidly because moisture convergence is actually declining. Circulation is weakening. So this is the point I want to remember, and this you have to remember because we have been taught for 100 years or longer that land sea contrast drives the circulation. Okay? If that is true, the land has been warming much faster than the ocean over the last 50 years. Okay? Because land has a little heat capacity. That has not increased circulation, that has decreased circulation. So that straightaway knocks out any attempt to connect circulation to land sea contrast. Okay? And what is limiting the rainfall from not increasing at this rate is that moisture convergence is going down, and just because your moisture available is going up does not guarantee you get more rainfall. Okay. Now the standard procedure in almost all papers published for the last 20 years is to resolve del dot QV into del dot Q prime V and del dot QV prime. This is the perturbation in moisture, this is perturbation in wind, and the traditional way of doing it, almost everyone, is that this is thermodynamic with dynamic. Okay, but that's wrong. But it is very popular in our field. Why is it wrong? Because how do you know V prime is not driven by thermodynamics? Okay, so this Neeland is the only guy who has been arguing that please don't arbitrarily resolve Q and V as two different sources. Q is to thermodynamics, no question about that. but V is both due to dynamics and thermodynamics. Okay? So this way of resolving does not really explain anything. This is convenient. Okay? A plus B, you do that, but that is not the real physics. Okay? Because people have shown that the convective mass flux is constraining the amount of rainfall, not dynamics. This is what is constraining, and that's ultimately related to not in the interseasonal scale, but on a monthly longer scale, related to energy available. Okay. Okay, let's go to forecast coming week. All India forecast is saying that it will continue to be high for a few days and then it will decline. Okay? This is a bit surprising, but overall, one gets the impression that monsoon is weakening, but they are showing for 4 to 5 days. Let's see next week whether they are true or not. Now, this is the ends up GFS forecast, and I see a very interesting difference between this week and the next week. This week, this event, you already saw this, there's a lot of heavy rainfall events. It will flip next week, okay? So let's see that coming true now. That is 28th July to 3rd August, it will start decrease in rainfall. Now, this is consistent with what I showed last week for East and WF, okay? Same thing. And what I like with WF, because they show the entire, from Japan to India, I'm sorry, this is coming week, this week, 21st, 28th. They're showing the rainfall anomaly is not local, it is extended up to Japan, followed by less rainfall. There's a part of the low frequency that was discussed by Ritesh. It's a part of that. Okay. Now this is this week. You go to next week, it disappears. Okay. 4th, 11th August, you see there is completely low rainfall here and high rainfall here. And this will move northward now. You will see that happening in the forecast. You can see this persisting for the next week. Sorry, I should have put this earlier. The 20th till 4th. I made a mistake there. Yeah, this after this would have come this, and then this one, settling further. Okay, and then you go to 11th to 18th August. It's still less rainfall, but a little weaker than the previous week. Okay, and then finally go to 18th to 25th. The new system is coming from below. Okay, so there's a clear indication forecast of low frequency northward moving one, which was discussed by Ritesh. Now this is 21st August, 1st September. Okay, it moves further north. Okay, so this is the prediction of EMW. We will see it in the next 1 month whether this is coming true. Now, the challenge is what will be the August mean rainfall? Because you can see half of August is up to 18th August is the core zone is negative anomaly. It flips to positive, not quite, and only end of August it comes. So I think August is below normal according to this forecast. Okay. Now, according to the July forecast that was made by IMD, I think they'll come out right. This portion will, we have seen already till about 23rd year, this is getting a lot of rainfall. So they'll come out true, and we have been getting less than normal. So this might come out more or less right. And Northeast has been below normal. Now, I just want to spend a few minutes for a new paper I saw, which is interesting. What they are doing is they are photographing SST in a region 20 degrees by 80 degrees and asking what the response of the whole climate is, or the whole of the tropics. Okay. Now, the colors mean nothing, just for convenience. Okay. Don't look at the colors. Colors don't mean anything right now. Now, their results are very interesting, which is what look at in the context of what Agni gave in his seminar, and in the context of the work Arindam and others have done. They are saying when they put warming in certain locations, these locations, okay, they show large density, that is, rainfall anomalies increase all over the tropics, okay, comparable to what happens in southern Europe, okay. But In these places, when they put an anomaly, the responses are not as good as this place. So the question is why? Why is such anomaly in some region introduced? There's an interesting logic here, which is worth looking at. Okay, so they make a following statement. This from Nature Climate Change 2 years ago. Warming and tropics is found that sandy regions produce a response larger than the usual propagation. Okay, and this will propagate vertically and transport it to whole globe. But if you do this in regions which are SHGs are not very high, and especially below 28, you will see nothing. Now, to me, there's a very interesting lesson here because this year, if you recall, we had a large anomaly here, extending all the way to US. Due to the reading its anomaly. I don't think it had any impact on the rainfall in the heart of the tropics. Okay, that's because these anomalies occurred in a region of descent. The region of descent, anomalies cannot propagate vertically. Okay, they are confined to the body layer, and usually there is an inversion aloft in those places. Okay? So it's a very interesting paper, and I want to highlight this paper because this is an idea which goes back to my student days, something called green function. How many have heard of green function? This was a way to understand how in a different equation, delta function reduced at some point influences the solution everywhere. Okay, so this putting these anomalies at a specific point is a way to understand how the equation respond to anomalies at specific location, and that can be related to the how the those equations behave. Okay. Now, although it was very popular in my student days, it is not that popular now only because that approach was very elegant, but it's strictly valid for linear systems. And over the last 50 years, we learned that the system we are dealing with is not linear. Okay, it's highly non-linear. So people are sort of giving it up, but I find some people are still trying to adopt it. Okay. I want to end with an interesting joke that the only thing in the news which is reliable today is weather. Everything else is a lot of fake news and wrong news. Okay, thank you. And next week it will be Samudra, right? Yeah. Okay, thank you. Any questions?
Yeah. And when you talk of increase in temperature and rainfall, the stability also changes. So that is not taken into consideration in this paper which you.
When the descending portion, the order of inversion. So we are adding acid anomaly of one.
No, the other one, the previous paper which you talked about.
Which one?
You showed the increase in temperature and the rainfall is not increasing at the same rate of temperature. And you only mentioned about moisture, but what about stability also comes into picture, which
That is totally like even critique about that which out there. That's all. That is not, I'm not telling anything. All I'm saying is it is too simplistic to resolve. There's going to be into Q kind, there's going to be unnecessary. It's okay for analysis of partial either, but to say that all the deep prime is due to dynamics running, and all the two dynamics are there. I'm not sure. Deep prime, I'm not sure.
But even
Deep prime also the wicked point.
even Q prime, for locally, for the Q prime, it not be everything thermodynamic. Locally, globally it's thermodynamic, but not locally.
Yeah, but these are just for global discussion. Yeah.
But that's not global.
There was large region, not over small region.
But even globally, and cannot be only thermodynamic, because for example, imagine a system where atmosphere is very, very strong.
Yeah.
With the tropics, we have much more gas and that is the subtropics. Right?
Yeah.
So Q will be high there. Right? With the even with the same circulation, Q can be higher. So the point is that I completely agree that V cannot be thermodynamic dynamic.
Yeah.
But even Q, I'm sure that it is not completely thermodynamic. Even dynamic will not be.
But until you get the Q, the chances of it being mostly much larger because
Yeah, but not locally. But I think locally it will be it will strongly depend on the consumption and weak convergence. That's what.
Yeah, can you show them, let me see some demonstration of that. And you're going to
But that can be seen from, our signal argument, yes, by Indian temperatures.
Yeah.
We are usually usually warmer
Yeah,
when it will be in drought years.
yeah,
But still we get a lower because we don't have a mass convergence, moisture convergence.
in day by one.
Even then, it only low at.
We're going to take over land. For land, I think we're going to other takers because if there is no rate for few days, not to drive down. Ocean, I'm not so sure. Let's look at the ocean. Yeah.
In fact, that significant
Huh?
analysis of the monsoon.
Huh?
There's a paper by May, I think she was spoken afternoon.
Yeah.
I think there is a paper,
Hmm.
and actually looked at that. I mean, she looks at the Indian monsoon.
Ah.
And in fact, the circulation is physically connected while looking at the global circulation and broadly have, let's say, four seasons week. In fact, you see a anomaly,
Okay.
which basically means the convergence actually increases in terms of delta V or
No, I don't want international scale or understand.
this is climate change. In climate change, basically, the
Which kinds of this container? Very long.
thing is over India, rainfall increases becoming over the climate change.
Yeah, isn't it because we have this container?
So people keep saying that this is because of the thermodynamic effect of increasing. But actually, if you actually look at the circulation, which is basically looking at just what happens to the gate river.
Like and so on, because how do you know that there's a consequence of,
No, that time.
Yeah, that's the problem. Yeah.
I think we have to say
Yeah.
end results.
once you drought, it's guaranteed you will have this. That's the problem. Problem is to resolve this extreme force.
Even these papers talk about causing effect. Tell them so. I think that probably about associations.
Yeah, also association.
Real causing
Yeah.
effect. I don't think we discussed that.
Even the British I want to ask, you have this saying that countries are the least expensive by something, country chapter. Okay? We discussed this a lot in the last 5-10 years. So do lots of checks to be, how do you know it's actually, it's not guaranteed. Because there are intention anomalies in SST and in the atmosphere, and there are people who papers completely confuse the heat in that. And I think you all know back, we don't have discussed that, okay, over the 10 years ago. Because both of them vary on the scale, right? Atmosphere and the SST. So to show which lead which is very tough. Because 15-day cycle, you will be thinking about what happened the previous cycle and interpreting it. So there is I forgot, we discussed that there is the Nobel Prize winners way of checking whether it is really leading and lagging, when the test of apply. Okay, don't did not say that. Because both of them have their own time series variation, and you put two time series, and both are varying psychologically, and you don't know which is leading to lag, not so very difficult. So, I mean, they were looking at economic, that's why that they were Nobel Prize for it. I couldn't put the name, I forget the name. Huh? Yeah. So you can think of just that, only then you can issue. But after the test and see whether it is really leading up. So it is very messy. Associate no problem. But if you say this is actually acting before that, that's very tough. But what you can do is you're doing your own simulation, you can fix the SST, and then that SST variable will go away. But in a covered model and the real data is very tough. So that's the problem with trying to connect convection and SST. It's always a tough problem. Okay?
Most of it.
Yeah, we will have a